Example 7.7 is going to see us approximating a definite integral using Simpson's rule. So let's have a quick review of everything that we've seen so far. We've approximated functions with rectangles, or rather we've approximated functions with constants. That's the constant, the height of that rectangle there. And then the area underneath that function is approximated by the area of the rectangle. That's a Riemann sum. We've also seen functions approximated with trapezoids. And now we are going to see functions approximated with parabolas. So maybe that's minus ax squared plus bx plus c, but some parabola is going to piecewise model our function. And Simpson's rule says that we can approximate the integral from 0 to 2 of 5x to the fourth. So this will be approximately equal to delta x. So I'm taking the interval 0 to 2, and I'm squeezing in 4 rectangles in my domain. So 2 minus 0 over 4, 2/4, or 1/2. So each rectangle in the domain will have a width of 1/2. So we have delta x 1/2 divided by 3. The division by 3 is a characteristic of Simpson's rule. And the left boundary point will be counted once. And then the interior boundary points will be counted alternating 4s and 2s. So we have 4 f of 1/2, 2 f of 1s, 4 f of 3/2. And when we get to the right endpoint of the domain of integration, we count it only once. So it's kind of like trapezoid rule, where the endpoints only get counted once, but what's different is you alternate between 4s and 2s for the interior heights. So running through this algebra, we have 1/6. Plugging 0 into this function, we have 0. If I plug 1/2 in and multiply by 4, I have 20/16. If I plug 1 in and multiply by 2, I have 160/16. Going ahead and getting a common denominator here. Plugging in 3/2 into the function and multiplying by 4, we have 16/20/16. And finally, plugging in 2 into our function, we have 1280/16. So running through the algebra here, we have 3080 over 96, or approximately equal to 32.0833. So Simpson's rule says that the approximate definite integral is 32.0833, roughly. Let's find the error by finding the actual true integral value. Right? This was an approximation using Simpson's rule. This will be the exact area between 0 and 2 underneath the function 5x to the 4. Right? We didn't really need to approximate it in the first place. We can easily find an antiderivative by going up a power and dividing by the new power and evaluating this antiderivative at 0 and 2. So this becomes 2 to the 5th, or 32. So our error is the absolute value difference, because I don't care who's bigger or smaller, of the exact answer minus the approximation, leaving us with an error of 0.0833.